last sessions, we talked about kernel optimizations on the kernel level, and in this session, I want to show you some optimization on the actual thread level. So this session will deal with the thread level optimizations. And we have 3 levels: the C++ level, the PTX level, and the instruction level. I will show some examples for this. Yes, switching to the code. So I want to start with an example that I had when writing some part of the MSM algorithm. The second or the third part of the MSM is summing up all the buckets after we accumulated the points into the buckets. What essentially you need to do is to go over some segments of an array, and let's say you have 8. You have a segment of size 8, so you need to sum the first element 8 times, and then the second one 7 times, and 6 times, and so on. And for this, you can do it with an algorithm with a running sum. So what you do is you do the first element, and then you do the first and the second element, and you sum the running sum of all the elements, you sum it together. So you have the sum and the sum of sums. And this saves some additions. If you save this running sum, if you save it separately, it saves many easy additions in this case. But however, when I tried to run this kernel, I encountered really bad performance, and I will show you what I mean. So this kernel, when I want to run it, the segment length is 8. I'm running the projective type. I'm running the segment sum kernel. So when I run the kernel, the time that it takes for it to run is 13.8 milliseconds. And now I want to compare it with the and over here you can see we have in the kernel we have 2 easy additions in each time this loops runs. We have 2 easy additions per iteration. And the easy addition is the most heavy computation stage here. So if we reduce this to only a single easy addition, we would expect around half the time. But what we get compared to 13.3, we get 2.7. So actually this represents the good performance, and once we add a second DC addition, instead of getting twice the time, we get about 4 times the time. So can you think why is that? Well, what's the problem here?
Is it dependency between the second and first edition?
Yes, there is a dependency. But why would that matter?
Matters that, for instance, when like storing to the local memory of the thread, you need to wait for the store to complete instead of just sending it and continuing to your next edition.
Mm-hmm. Yeah, actually, right, because you're storing in the register memory. But I mean, yes, that's close to it. But actually, the compiler could realize that that at any given moment you need to store in registers only the two elements that you sum, and then the extra one you can keep somewhere else, maybe in shared or in global or in cache. So theoretically, it could be better, but actually, the thing is most probably because the AC addition uses many registers, it doesn't have enough space in the registers to perform that. And we can see it in the Insight compute reports. So if I look at report 80, this is the report for the single addition. And you can see the compute throughput is 75%, which is high. And the amount of registers used is 234 registers. And the maximum per thread is 255, actually. So it's close to the max. The amount of registers also limits the occupancy. We can have only 16% occupancy. And once we go to and do two EC additions, then the compute throughput goes down to 35%. And you can see the memory throughput isn't high. So it is actually compute bound, this kernel. And the registers goes up to 255. So that's why I think it's probably due to the register pressure, that we don't have enough room in the register space to keep all the results. And that, yes, and because of that, the compiler needs to do some extra like gymnastics to perform this code. If we look at the PTX also, then we see that this kernel with this single EC addition, it's around 6,600 lines of PTX code. And as expected, the one with the two EC additions is around 13,000, which is about twice. So this is a problem that I tried to solve in many different ways, and I actually haven't really come up with a solution to this problem yet. Yes, I managed to come up with alternative solutions, and also this problem can be avoided in some similar cases, but not quite this case. So yes, so first I wanted to show you another kernel where the EC additions are not connected and not dependent. If we look at this multi-addition kernel, what this does is just each thread takes a few elements, reps number of elements, and adds the same element to itself, and writes it to the output. So if reps is 2, it will take 2 different elements and do the addition and insert them to the out in the global memory. So currently this loop will be unrolled. What does it mean that it's unrolled? It's like I don't have the loop, and I just write explicitly all the loop. What I will get here is that if I run this kernel with which one is this? Yes. So if I run this kernel with a single EC addition, then we get this time 3.1, which is quite similar to the time that we got before for a single EC addition. And if I run it with 2 times, then if it would be okay, I would expect actually to get the same time, because in this kernel, when each kernel does each thread does 2 additions, but it's in total it's the same amount of additions in total. So I would expect the same time, but you will see that I get actually double the time, which is the same problem as we saw before. Yes, so we're getting double the time. But there is a solution for it in this case, which is actually to not unroll the loop and use unroll 1. This tells the compiler not to unroll the loop. And once we do this, then the PTX file that we would get would be also around 6,000 lines, the same length as a single EC addition. And it will contain only a single load and store. So I want to show you the relevant PTX files. This is the PTX file for a single addition. And if I search for the load from global memory command, let's see I have 10 results. So, and this is the amount of commands that you need to load a single point. And this is, yes, so this is the PTX for the single addition. For the one with the 2 additions, we see that we have 20, meaning we are loading twice for the 2 EC additions. And this, so that's the report for the unrolled loop. And this is for the loop that isn't unrolled. We see that we have only 10 LDG commands, meaning that we're loading only a single point. And we have an instruction that tells us to loop. And this code, as I said, is a similar length to the PTX code for a single EC addition. So what that means is when using EC additions, it would be preferred not to have many EC additions in a single kernel or in a single piece of code that isn't unrolled, because we see this gives really bad results in comparison. What I did in the end for the segment sum is I just use a different algorithm that uses only a single EC addition each time. For each thread, it does only a single EC addition and not multiple EC additions for the same thread. Any questions about this?
So it means you have double threads.
So it means I'll have more threads, yes.
And doesn't the threads have a dependency between them where it's so that half of them would run and then the other half would run?
Yes, I mean if you have many threads, then they won't all run in parallel. But
and therefore you get to factor 2 instead of factor 4.
It's fun.
yes, yes, exactly, because it will be fine. Because the problem here is the register pressure on a single thread, and this is the pressure per thread. So I think the main thing we can learn from it is that don't have too many registers in a single thread. And specifically, the EC edition is prone to this problem.
Also, if I can say something about what you said, Colin, the maximum number of registers that a thread can have is 255. Okay, so if you have like if you have fewer threads, it doesn't give you more registers. It just means that some of the registers are just not going to be used. Okay, so you actually want to go up to like going up with the number of threads to some limit where you still get the 255 registers is better use of the hardware. But also I think that there is still, the reason I said that like not yet before is that if you know that you're able to implement your thread with fewer registers, right? Then you could always go to actually writing the code in PTX. And I believe that you can also write the code in C in certain ways that will actually force the compiler to do garbage collection, and then it won't be able to inflate the number of registers. Like sometimes what you use is you actually close blocks in curly brackets, and you define variables internally in those curly brackets. And then when you go out of that block, then the variable has to be deleted. So I think that this kind of code writing could help in those situations where, like, because I mean, in this situation, I had an alternative, but you may encounter a situation where you don't have like an algorithmic alternative, but you still know that there is a way to implement things using fewer registers.
Yes, so a possible other solution would be to split the actual EC edition into multiple threads. So instead of a single thread doing EC edition, maybe do it using 2 or 3 threads. But that's a more long-term solution. We did try some attempts to fix this kernel, trying to use the shared memory. So we thought that if we each time store the result from the registers to the shared memory, and then each time we have only 2 values in register space, then maybe this would resolve the register pressure. And this is what I try to do in this kernel. However, it did improve it a bit, but not enough. So it raised the compute throughput from 35 to 40 or 45, but not back to 75. So yes, so from my experience up to now, it's actually hard to force the compiler to do what you want it to do using only the C++ level of code. Although there are some pragmas, as I shown before with the unrolled pragma. It's not necessarily straightforward. Another example for this is the entity. Well, actually, I just wanted to mention that this trick with the unrolled one is used in the entity code. If I look at the entity code, Let's see, yes, NDT64. Right, so you can see an example for it over here. This is good both for the PTX file, and it also, when you have a really long kernel, it could be a problem also for the program memory size. So this is another thing that this optimization could work for. So actually, this loop is not needed here, because in the first loop iteration, you do only the entity 8. You do the entity 8 and then this part of the shared memory transpose. And then the second iteration, you do only the entity 8. So you could have written it only entity 8 and transpose and another entity 8. But in order for the PTX not to be long and the entity 8 not to appear twice in it, we can do it inside a loop and unroll it, make sure it's not unrolled. So we are using this trick in the entity code. So a different example is the thread entity. So in our implementation of entity, we have a thread entity that does entity 8. An entity 8 naively looks something like this. This is actually an entity 8 without the twiddle factor multiplications, only the additions and subtraction. So it's composed of 3 stages. In the first stage, you do plus minus with 0 and 4, 1 and 5, 2 and 6, 3 and 7. Then you do it with 0, 2, 1, 3, and then with 0, 1, 2, 3, and so on. So this code actually initialize like 8 extra variables. So I go from the x's to the y's, and then from y's to x's, and from x's to y's, and then at the end I need to go back from y to x, because this function is by a reference. So I need to return the x's. And I saw this and I thought that maybe it's not good to use so many extra variables, because it will lead to extra registers. And I want to save the register memory space. So this is an alternative way to write the same computation. This time using only a one extra temporary variable. So the variable here are switching only within the x variables with one extra variable t. So it's a more optimized way in terms of a number of variables. But actually, when testing this, so this is a kernel that just does multiple entity 8s. So it reads from 8 elements from the global memory, and then does an entity, and then writes the 8 elements back. So let's see the performance of this. Well, first the regular entity. So I want to use the scalars. And the entity kernel. So we get 0.336. And when we use the optimized version, we actually get 0.35, which is worse. It's not, yeah. It's actually the same. The time changes a bit. But actually, we get around the same time. We don't get any improvement. So how could you explain that?
The compiler saw it. He did it.
The what?
The compiler saw it and did it behind the scenes.
Yes. So actually, the compiler is smart enough to take the C code and then do many optimizations. So in this case, it didn't really matter how I wrote it. And actually, if you look into the compute reports, actually this one uses more registers than this one. So it just explains this point that I wouldn't recommend trying to optimize the thread level using the C++ level, because it doesn't always work as you think it does. And there are many levels of the compiler, because the compiler compiles this first to the PTX level, and then per GPU architecture, it compiles the PTX level to the actual instruction level. So indeed, when you want to control the specifics, then you write PTX code. And there is a way to write PTX code directly in CUDA. And we do this in Icicle in the field code. So if we go here to field.q, we see how is our modular multiplication implemented. It's a function that is called actually operator. It's overloaded the field multiplication, and it's composed of a multi-precision wide multiplication, and then a reduction step for the modular operation. This mul-wide function uses the multiply raw, which uses the multiply raw device, and we implement this with actually a Karatsuba algorithm. But when you go into all these functions, in the end, you will encounter these types of functions, which refer to the PTX namespace, such as this function, which uses the ASM function, which can, and in here you can write the actual PTX code. And NVIDIA has the documentation of exactly all these low-level functions and what their arguments are. So in Icicle, all the modular multiplication is basically written in PTX, so the compiler can't change it a lot. It's predictable. So that's a bit about the PTX level. Let me see if I wanted to go over anything else. Yes. So for my final example, by the way, any other questions before I go to my final example? Okay. So for my final example, I wanted to show you a simple multiplication that is implemented in the PTX level. This multiplication is for the case where the field size is 64 bits. So it's composed from two limbs of 32. So it's an array of 2 elements of 32. We have A0 and 1 and B0 and 1. And the result will be R0, 1, 2, 3. This is the kernel. What I'm doing is I'm getting arrays of uint 32. And I'm reading 2 elements into the result array. And I'm multiplying the result by itself and inserting the result back into the same variable. And I'm doing this multiple times in order to see only the compute throughput without the memory. I will actually do it around 200 times. Yes, so 200 times. This time I'm using uint 32, and I'll use 2 to the 25 elements. Okay. So what I wanted to show you first is that this multiplication, I'm calling it the naive multiplication. Let's see what it does. So R0, which is the lowest bits, is the low multiplication of A0 and B0. So A0 and B0 will give us a 64-bit result. And the low part will go into R0. The high part of the same multiplication will go into R1. And then R1 needs to get also the low part of A0, B1, plus the result that was there before. So this is MAD is multiply add. And then we will have to add also the low part of A1, B0. So yes, so this is actually a school book multiplication. This is the naive algorithm. But actually the one in Icicle, you will see that it contains more PTX commands. But let's see now which one gives the better performance results. So if I measure first the naive multiplication, I will get 0.45. No. Yes, I knew there was something wrong. I wasn't using the correct kernel. So I will get around 2 milliseconds. But when using Icicle version, it's actually faster. And actually, we have the same amount of multiplications, but the Icicle version is actually longer, has more instructions. So at first glance, this is a bit strange. And what is the explanation for this? So this I learned from Niall Emmott. He has a paper about this, and also a YouTube presentation. And this actually has to do with the lowest level, the actual instruction level. So the instruction of most recent GPU architecture, they have this instruction, which takes 32 bits, multiplies them, and adds them. So this is a multiply add, and it adds them with another 64-bit argument. And this instruction is very fast and can be performed in a single clock cycle. The thing is that it assumes the alignment, the low part is in an even register, and the high part is in an odd register. And if you have a different alignment, the compiler wouldn't be able to use this instruction. It will have to use multiple instructions to perform the same operation. And when you do a multiplication that is higher than 32 bits, that has many limbs, it will look something like this. This is an example of 4 limbs by 4 limbs. And when you do A0, the first 2 rows is the B0 multiplication. So you do B0, A0, and we get the low part of A0, B0, and the high part of A0, B0. And then we get low and high of B0, A1, and so on. And we get this pattern. And what you can see is that actually we have a problem with these lines, because in these lines you need to accumulate a low part into an odd register, an odd accumulator. So this will encounter the problem that it doesn't have a relevant instruction. And the solution that he offers is to split it into 2, and to accumulate these shifted terms into a different register space, and then to shift all the results together, and then to add them at the end. And that is actually what is done here in the Icicle version. So we take, and this is the simple example where we have only 2 terms. So we take A0, B0 and A1, B1, which are the even part, and we put them into the result actual accumulators. And then all the odd parts where we'd have A0, B1 and A1, B0, they're accumulated to a different array called odd. And only at the end, we add the both together. And it actually, you can see, it gives around 25, or not 25, around 12% improvement. But yes, in order to do this type of optimizations, you really need to be familiar with the very low level, the instruction level. So it's by no means straightforward. Okay. So before I sum this up, are there any questions about this last example, or any other questions?
So basically, the PTX library class, I don't know how to call it, has all the assembly functions wrapped like this.
So the PTX is not is something that we wrote.
Okay.
Um,
You do actually
it
write it in text.
Yes, it encapsulates many of the actual low level, and we can add here more functions as we like. Okay.
Is it more specific for problem of computations which will use more register memory?
This doesn't depend on the register amount, because here I showed it. It's actually only 2 registers per element.
It's something like what the kind of computations for which you want to actually do something like this.
So I wanted to say a few words about that, and I want also to again to recommend where is it? I wanted to recommend the best practices guide. Yes. And to say a few words to sum up the entire mini course, which actually I went in a quite similar way to this best practices guide. This also recommends when optimizing an application, first you need to go from the high level and down. So the most crucial optimizations are the parallelizing your code and actually turning it into kernel calls, so it will be parallel. And then doing all these using streams and copying and parallelizing data transfer with actual computation. Then you can go and dive into all the memory optimizations, which I showed you regarding coalesced reads and writes using shared memory. And also you have the type of optimizations where you don't want thread divergence, you want to reduce their conditions, you want the threads to do the same type of work. And those are all the optimizations that you look at the kernel level. And only after you finished all of those, that is when, for even more performance, you need to go to the specific thread level optimizations that I talked about in this session. Once you optimized everything else, then you try, and there are some tips in this guide also. Like you should avoid using the modular operation because it's a bit more expensive. There are other tips, using signed instead of unsigned. And this is also a high level thread level optimizations. When you go down to the level of the actual PTX and the instructions, it's mainly you need to have a really deep understanding of it, or you do many trials and errors until you get that understanding. Okay. Yes, so that's about it for this session. I hope this course was helpful. All the recordings will be available. Yeah, so thank you.